Okay, good morning all. So in the last lecture, we were looking at some definitions related to graphs. So we were looking at the definition of path, simple path, cycle and simple cycle. A path is any, uh, when you try to connect a sequence of nodes which are already connected with edges, when you are trying to draw a line over a sequence of nodes which are already connected by edges, it can be as complex as you want. That is a path, as arbitrary as you want. But the only condition is you should connect only those nodes which are already connected by edges, and you should not lift your pen. That's all. So you can repeat any number of nodes, you can repeat any number of edges. It can be as complex as you want. Everything is a path. All right. It is a simple path if no node is repeated. Okay. So basically, it's like an open path. No node should be repeated. In case a node is repeated, and if that node also happens to be the starting node and the ending node, okay, you're not going further, you're not stopping before. In that case, it is called a cycle. So a cycle is nothing but a path where the starting node and the ending node are both same. Now, a simple cycle is one where no other node is repeated. A simple cycle is a cycle where starting node and ending node are same, but no other node is repeating. So we saw the example, right? So in this case, this is the starting node and ending node, and no other node is repeating. Fine. So this is a simple cycle, only if you look at the red cycle. All right. But if you consider this blue one, you see, you started here, you went like this, then like this, you visited this node, and you again crossed this node, and you came back to the starting node. This is a cycle because the starting node and ending node are same, but this is not a simple cycle because you have revisited some other node also. Okay, so there is some crossing of at some other node. So this is not a simple cycle. In this case, there is no crossing at any other node. Only this starting and ending node you have repeated, no other node is repeated. So this is a simple cycle. If you repeat, apart from the starting and ending node, if you repeat any other node in your cycle, then it is not a simple cycle. Okay. Now you consider the green one where this is the starting node, and you went right, you came down, again you went up, and you went left, and you stopped here. Okay. So here, is this a cycle? No, because the starting node and ending node are different. A cycle is a part of this path. Okay. But this path itself is not a cycle. It started somewhere, it ended somewhere. So it is not a cycle. And definitely it's not a, what do we say? It's not a simple path. Even if you consider it to be a path, it is not a simple path because there is a repeating node. So the starting node, you are revisiting when you are going back. Fine. So it is neither a cycle nor a simple path. It is a path. That's all. If the starting node and ending node are same, then it is a cycle. So in this case, a cycle is a subset or a subpart of this path. This path is not a cycle. Okay, fine. Then there are two more definitions, so you can write them down. So what is a tree? A graph is a tree if it is connected and has no simple cycles. Fine. We all know what a tree is. A tree is a kind of a graph, but a specific kind of a graph. It should have no cycles. All right. Simple cycle. The concept of a complex cycle will come only when you try to draw a path. Suppose you are not trying to draw a path. The graph is the way it is. Okay. In such a graph, there is no concept of a complex cycle. There can only be simple cycles or no simple cycles. That's all. Like if you consider this blue path, you see this is one simple cycle, this is another simple cycle. You chose to draw a path which involves these two simple cycles and it became a complex cycle. That's all. But there is no inherent structure as a complex cycle itself in the graph because there are only simple cycles in the graph. You may want to connect these two simple cycles or some other two simple cycles. I may choose to connect, instead of these two simple cycles, I may choose to connect this simple cycle and this simple cycle. So it is me who is connecting two or more simple cycles to form a complex cycle. So a complex cycle is constructed by us. It is not there as a complex cycle in the graph. In the graph, whether you draw or not, there are simple cycles or there are no simple cycles. Okay, but complex cycles can come only if you try to draw. If you don't try to draw, there are no complex cycles. Okay, so simple cycles are given to us, complex cycles are given by us. Okay, that is why here in the definition it is said it has no simple cycles, because simple cycle has nothing to do with the path, where it starts, where it ends. It doesn't matter, because these three nodes, they are interconnected. So it is a simple cycle. Whether you start the path from here or from here or from here, it doesn't matter. Okay, so simple cycle is either there or not there. Whereas complex cycle, just by looking at the graph, you cannot say there is a complex cycle. If you choose to trace that path, then you have traced the path of a complex cycle. If you choose not to trace that path, there is no complex cycle, right? So that is the reason why here in the definition it is given a graph is a tree if it is connected and has no simple cycles. Okay, if there are no simple cycles, obviously there can't be a complex cycle also, right? That's all. So everything is built out of simple cycles. Complex cycles are built out of simple cycles. Okay, then root. So what is a root in a tree? A root is nothing but a specially designated node in a tree. So there is nothing inherent in a root node which necessarily makes it the root node and not something else. You can make any node a root node. That is purely your choice, right? So suppose I have some structure like this. Say, now what is the root node in this? Usually we are used to say like 1 is the root node, right? Because it is drawn like this. I can just redraw the same tree in a slightly different way. I can draw it like this. 3 to 1. If I had shown you this tree first, instead of this tree, what would you have thought? You would have thought 3 is the root, right? Right? But these both are same trees. I just rearrange these nodes to get this structure. All right. So there is nothing inherent in a tree or in a node which makes that a root node. Okay. So just because you drew a particular tree in a particular way does not necessarily make a particular node the root. So actually, when we say something is a root, we have just chosen that to be the root. That's all. So although this tree is drawn like this or this is drawn like this, I can choose this to be the root. It's up to me. You cannot say, no, it is at the bottom. How can you choose that to be the root? Nothing like that. Once you choose the root, relative to that, the rest of the tree is, you can restructure, you can redraw the tree in a different way or whatever, but it is all relative. There is nothing absolute about the root or absolute about the children. Fine. Once you decide the root, everything else falls in place. Okay. So let's continue. Okay, the next definition is that of leaves. So how do you define leaves of a tree? Nodes with no children. Okay, but we didn't define the concept of children yet. So with whatever definitions we gave so far, can you define leaves of a tree? Node with just one connection. Okay. sometimes root can also have just one connection, like in the previous example. Then what about that? So
non-root node with only one connection.
exactly, that's it. So we all know the leaves of a tree are those which have no further children, right? But we didn't define the concept of children. So technically, when we say they have no children, what we are saying is they have only a parent. And usually in a tree, no child can have more than one parent. And first of all, in an undirected tree, there is no concept of child and parent. All right, unless you sort of define the root. So only one parent means only one node, one edge. Okay, one connecting edge, which means its degree is 1. So those nodes with degree 1 are called the leaves of the tree. But sometimes root node can also have degree 1, like in the example which I showed just now, right? Just 3 nodes in a line. If I consider a top node to be the root, it has degree 1. But that is not called a leaf. The third node in that sequence is called the leaf, because that also has degree 1. So to put it simply, the leaves of a tree are those nodes with degree 1 except the root node. That's it. Okay. So the nodes of degree 1 in a tree other than the root are called leaves of the tree. Okay. So suppose if I consider a tree like this, so what is the root in this tree? What is the root node? Hmm? Anyone? One in the center. Any other answers? Yeah, you were saying something. Any node. It's my choice. There is nothing special about any node here for it to be a root node. It's not necessarily the center node or the top node or right bottom or left bottom, nothing like that. I can choose any node to be the root. It's up to me. Okay. So whenever someone asks you the question, what is the root node in this tree? You should ask in return, you tell me. That's all. There is no correct answer for that question. Or I will choose anything. That's all. Okay. So there's no right or wrong answer for this. You can choose any node to be the root. Suppose I will choose this node to be the root. All right. Let me number this. So this is 1, 2, 3, 4. So what are the leaves of the tree? One and 3. That's all. Because other than the root, only these two nodes have degree 1. That's it. So this is a leaf and this is also a leaf. Okay. No. Here it said nodes of degree 1 in a tree other than the root. Because it will be a root node, first you should define a root node. Other than root, it should be only if it is other than the root. See, in that case, it's up to you how you define your convention. If you, in your system, if you if you are okay with a root also being a leaf, you can say a single node tree. That same node is both the root and the leaf. If you if your convention is that root node cannot be a leaf anytime, then in that case that can be only root, cannot be a leaf, because you should definitely have a root. So it can be root and not a leaf. That's all.
Why does that mean that leaf node is the one which doesn't have a children? By that definition, that is the leaf node.
That's what I'm saying. But the definition also says it should not have children and it should be different from the root. If you want to come up with a definition where the second condition is not important to me, only condition is it should not have children, I'm okay if the root is also a leaf. It's fine. It depends on the system. It's basically a convention. Yeah. Okay. So the next definition is that of. So far we looked at undirected graphs. So now we will look at directed graph. So a directed graph is a graph that is a set of vertices connected together where all the edges are directed from one vertex to another. So we all know, like any simple example, suppose there are three nodes. In an undirected graph, we cannot have more than one edge between two nodes. Can we have more than one edge here? Yes, if they are in the opposite directions. So for instance, if you take these two nodes, there is an arrow in this direction. You can have one more edge or arrow in the opposite direction. Okay. But in the same direction between the same two nodes, we cannot have more than one arrow. All right. So you cannot have another edge like this. So this is not possible. Fine. So maximum two arrows are allowed between the same pair of nodes in opposite directions. That's all. Okay. So for an undirected graph, we spoke of degree of a node. Since this is a directed graph, we have to distinguish degrees into two types: out degree and in degree. So what is out degree? What is out degree? Yeah, that's it. Number of edges going out of a node, outgoing from a node. That's all, right? The number of outgoing edges okay. And what is in degree? Similar. What is in degree? Number of incoming edges into a node. That's it. Okay. Next, directed path. In an undirected graph, there is no concept of direction, so you can go in any direction as long as there is a path between, or there is an edge between two nodes. But here, apart from the existence of an edge, that edge also has a direction. So the direction in which you trace your path also matters. All right, so it is always a directed path. So what is a directed path? A path in which all the arrows point in the same direction as its steps. Okay, so if we take this graph, suppose suppose I try to go like this. Okay, just this. Is this a directed path? Why no? I go from here to here. I need not draw an arrow. I'm just going. So is this a directed path?
Yes.
It is yes, because there is an arrow in this direction. Okay, suppose if I continue, if I try to go like this, is this a directed path? Is this a directed path?
From that to direct.
Yes. So let me number them so that it's easy. Let's say this is 1, 2, and 3. So I'm trying to go from 2, 3, 1. So 2, 3, 1, is it a directed path? No, because 2, 3 is okay. There is an arrow in the direction, but 3, 1, there is no arrow in the direction. The arrow is from 1 to 3, not 3 to 1. So that is not allowed. Your entire path should have arrows in the same direction, and they should point in the direction in which you are going. They should be in the direction of your motion. They cannot be in opposite direction also. All right. So 2, 3, 1 is not a directed path. All right. Now suppose I try to go like this. Is this a directed path? Yes, because 2, 1 and 1, 3, they are in the same direction. And also they are in the same direction as your motion. So that is a directed path. If I continue this, is this a directed path? No. It is, because you have an arrow from 3 to 1, 3 to 2 also. You have one arrow from 2 to 3. You also have another arrow from 3 to 2. So this is a directed path. All right. So simple. All through your path, the arrows, there should be at least one arrow connecting every two nodes in the direction of your motion. If at any point you don't have an arrow in the same direction, then you're stuck. You can't proceed further. That is not a directed path. That's all. Okay. So For example, I can say 1, 3, 2. This is a directed path. 2, 3, 1. This is not a directed path because there is no arrow between from 3 to 1. Fine. That's it. Or to put it simply, 1, 3, 1 to 3, there is a path. So this is a directed path. Whereas 3 to 1, there is no path. There is no arrow in that direction. So this is not a directed path. Okay. Fine. So and so on. All right. Next definition is strongly connected graph. So what is it? A directed graph is said to be strongly connected if it has a directed path which connects every two nodes. So what do we mean by that? Let me give an example. So let's assume I'll just quickly draw as points. Okay, now, so what is meant by this definition is you start from any node. If you are able to reach every node via a directed path, then that graph is said to be strongly connected. So for instance, suppose I start from this node. I can reach this node. I can reach this node. I can also reach this node. I can also reach this node. So from this node, I can reach every other node in the graph. Fine. But this is only from one starting node. You should check with every other node as a starting node. So this is okay. There is a directed path from this particular node. So let me again number them. 1, 2, 3, 5. So from 1, I can reach every other node. Now I should also check with 2. From 2, can I reach every other node? No, I can reach 3, 4, 5, but I cannot reach 1. Okay, so this is not a strongly connected graph. Suppose if I want to make it strongly connected, suppose I have some path like this. Now from 2 also I can reach every other node. Fine. Now suppose instead of this, now from 2 I can reach every other node, but from 3 can I reach every other node? No, right? So again, there should be some method of making the graph strongly connected. So let's assume, suppose I have an edge like this. Now from 3, can I reach every other node? Yes, right? From 3 I can reach 1. Through that I can reach 2. Then I can again come back to 3 and I can go to 4 and I can go to 5. So I can reach every other node now. Fine. From 4, can I reach every node? No. I can reach only 5. Right? So one way is I have an arrow like this, either to 3 or to 1. Okay. Now I can reach every other node. 4 I can, from 4 I can reach 3 and I can reach 1, I can reach 2, again I can come back here and I can reach 5. Okay, that is one way. Or let's assume we remove all this. I remove this, I remove this, I remove this also. I just have one arrow like this. Now I can reach every node from every other node using a directed path. From 1 I can reach 2, 3, 4, 5. From 2 I can reach 3, 4, 5, 1. From 3 I can reach 4, 5, 1, 2. From 4 I can reach 5, 1, 2, 3. From 5 I can reach 1, 2, 3, 4, 5. That's it. So the graph can be any way. Sometimes you may have a complete directed paths only from a few nodes. Sometimes you can have complete directed paths from every node. So when from every node you are able to reach every other node using a directed path, that graph is said to be strongly connected. That's all. Clear? Fine. Okay. Let me know if you have any doubts. All right. So the next topic, which is an important for this course, that is strings and languages. So one thing you should keep in mind throughout this course, we don't make a distinction between a word or a string or a sentence. All three are same. So there are only two categories in this course. One is letters, another is sentences. There is no in between words. Normally in language we have three categories, right? Letters, words and sentences. Here there is no distinction between word and sentence, because the so-called distinction between word and sentence is coming because maybe you are using a space between two words or a comma between two words, something like that, as a special character. But if you think from a programming perspective, I can store these two words also in one array, in one string, right? So technically, whether the two words are separated by a space or a comma does not matter to the computer. That so-called space and comma is also a letter, like any other letter ABC. So this entire thing is like one string for the machine, right? So it does not make a distinction between a word and a sentence. We make a distinction because we consider space to be a special character, comma to be a special character, punctuation marks. We distinguish between punctuation marks and regular symbols. But a computer, every symbol is a regular symbol further, right? Including punctuation marks, including spaces, including commas. They are like ABC. So this entire thing is like one string. You can store it in one array. It's not like it will not force you. No, this word is separate, this word is separate. You have to store this word only in one string or one array, this word in a separate array. It doesn't force you like that. It can take this entire string in one array, right? So technically, there is only a string. Even if it has spaces or it does not have spaces, it is one string. So a string or a sentence or a word are all same for us. The only other category is individual letters or symbols. That's all. There is no concept of word in between. Or even if it is there, it is not different from a sentence. Okay? So what is the basic unit with which you construct a language? What are the basic units called? Letters, symbols, right? So any language should start with a set of symbols, which we call as an alphabet set. Okay? Sometimes we use by mistake alphabet to refer to each letter in the language. That is not technically right. Alphabet is the entire set of letters. So we say there are 26 alphabets in English. That's not correct. There are 26 letters in English. That entire set is called alphabet of English, English alphabet. That's all. So alphabet is the set, not each letter. Okay. So the first definition is that of alphabet. So what is an alphabet? A non-empty, finite set of objects called symbols. So here, both these words are important. It should be non-empty and it should be finite. If any of these conditions are not satisfied, it cannot be an alphabet set. So, for instance, if you consider, say, natural number set, it cannot be an alphabet set because it is infinite. All right. And second thing, each of the natural numbers themselves is built out of some digits. So I can take a big natural number like 1,27,532 something. Now this is actually not an alphabet or a symbol. This is a sentence. This is a word built out of symbols or letters or digits, where we have finite digits, 10 digits, 0 to 9. So this set of digits 0 to 9 is the alphabet set for constructing numbers. That's all. And it is non-empty and it is finite. 0 to 9, there are only 10 symbols and they are finite. Okay. So using these digits, you construct any number. So the set of natural numbers, the set of sentences which you can construct can be infinite. But the set of letters which you start with, your atoms, should be finite. Okay. The number of digits 0 to 9, they have to be finite. You can't have infinite sequence of digits. So the alphabet set should be finite, whereas the number of sentences and the different types of sentences which you can construct, they can be infinite. All right. So natural number set is not an alphabet set. It is a language. We will come to what a language is. Set of sentences which you can construct from an alphabet set is called a language. So natural number set is a language, one possible language which can be constructed out of the alphabet set, that is 0 to 9. Can you tell me another example of another possible language that can be constructed using this alphabet set 0 to 9? Yeah, integers also.
But it has a concept of
negative. So there is a symbol like minus. So you have 10 symbols 0 to 9 plus one more minus. Then you can construct the set of integers. But suppose I don't have that. I have only numbers 0 to 9, digits 0 to 9. From this set, what other language set can I construct other than natural numbers?
rational numbers.
Whole numbers? Not rational numbers?
Positive rational.
No, even that.
We can represent them as in fractional form.
But that fractional form should have some other symbol, right? Prime numbers? Yes. Prime number set, even number set, odd number set, Any subset of natural numbers is another language. Octal, yes, no. Octal you can, but someone should say this is octal. See, that is where you interpret a number. Fine. So octal, decimal, all these are the ways you interpret a number. Like suppose if I give you 1 1. Now I can tell you whether this is binary or this is decimal. Depending on it, its meaning will change. But the number 1 1 is syntactic. Okay. So in that sense, it has nothing to do with octal or decimal or binary. 1 1 you can construct using 0 and 1 or just 1, whatever it is. Okay. So in that sense, you can construct natural number set or even number set, odd number set, or whole number set, or any subset of natural numbers, multiples of 3, that can be a set, multiples of 5, or prime number set. All these are all different languages that can be constructed out of the single alphabet set, that is 0 to 9, these 10 digits. That's all. Okay. Yeah.
So do we define meaning of the language separately?
Yes, sort of. Meaning is not part of the language set. So you can construct some arbitrary sentences which may not have any meaning at all, or which may have multiple meanings. So the interpretations are given over and above the language. So language maps to a meaning, but meaning is given by us. And meaning can't be generated in such a simple manner as the way we will generate languages. You will see in the course. So you can generate sentences. You can generate, so a set of sentences will constitute a language. So you can generate a language, but you can't generate meanings. That's a different complex process altogether. Okay. Yeah.
Can we just say, so essentially a language is a set containing all possible
symbols.
Yeah.
Combinations of symbols. Yeah, combinations of symbols. Exactly. So language is a set of combinations of symbols. Language is a set of sentences. A sentence is nothing but a combination of symbols from the alphabet set. That's all. We'll look at all those definitions slowly. So usually the alphabet set is represented by the Greek letters sigma or gamma. This is capital gamma. Okay, so let's look at some examples. Like sigma 1 is just two symbols, 0 and 1. Sigma 2 can be the entire English alphabet set, and maybe digits 0 to 9. So 36 letters or 36 symbols. Maybe one more alphabet set can be just say A, B, 0, 1, or some other set can be some arbitrary symbols, maybe some punctuation symbols. Okay, so now from each of these sets, using each of these sets, we can construct different kinds of sentences. Suppose using 0, 1, maybe I can construct a sentence like 0, 1 or 1, 1, 0 or anything. I can also construct an empty string. We will look at empty string later, but that can also be. It's like the alphabet set should be non-empty, but from this non-empty set, I can choose to select at least one symbol or no symbols at all. If I choose to select no symbols from this non-empty set, I will get an empty string. That is called epsilon. We will look at that. We look at that later. So here each of these is a sentence, and usually a sentence is represented using another Greek letter, omega. Okay. Say similarly, from this alphabet set, we can construct some sentence like this, whatever. Okay. Now again, this is a sentence, or also called a string, and represented using omega. All right. So we can construct umpteen sentences or potentially infinite sentences from a finite set of symbols. Okay. Now, out of all these potentially infinite sentences, we can take a subset and call it a language, or we can take this entire set also and call it a language. That will be a universal language that can be built out of these symbols. But usually we take a subset of these universal languages, universal language. We take different subsets. So those languages we use, like natural number set is a subset of universal language that can be built out of zeros, ones, and all that. Whole number set is also sort of a subset, in the sense, you see, I can have 0, 1, 2, 3, and so on. I can also have 0, 0, 1, 0, 0, 0, 0, 2, like that. These sentences can also be constructed from 0 to 9. All right. But I just take 0, 1, 2, and so on. I don't take sentences which start with many zeros and then followed by a digit. I don't, even if I take, I don't consider them as different numbers, right? But this is again an interpretation. For me, 0, 1 is same as 1, or 0, 0, 1 is same as 1. But these are three different strings in the language. 1 is different from 0, 1, that is different from 0, 0, 1. Technically, there are three different strings. Okay. It is a different matter that you are treating all these three different strings in the same way, but that's a different thing. But technically, there are three different strings. So if you take only one from these three strings, you're ignoring 0, 1 and 0, 0, 1. It means your set is a subset of all the possible strings that can be generated from this alphabet set. That's all. Okay. So, okay. So anyway, any doubts so far? It's quite simple. It's like any language which we use. Each language is constructed out of the basic units of any sentences or words in our language are letters, which we call as the alphabet set. You combine those letters in all possible ways, right? Some of them may be useful, some of them may be meaningful, some of them may be meaningless. Like in English, you take these 26 letters, you can arrange them in any arbitrary way, right? I can just put some letters like R, B, U, X, something, T, W. This is also a sentence or a word constructed out of English letters. But we don't consider it an English word because we don't assign a meaning. Okay. But many such infinite sentences can be constructed out of English letters, out of which a subset of those sentences we consider as valid English words. So whatever we call as English language is a set of words which is a subset of all possible words. Whether that word has a meaning or whether that word can be pronounced or not is a different thing. But any sequence of letters is a word. Out of all such possible words, we are taking a subset and saying, okay, these words are part of English language. These kind of words are not part of English language. That's all. Okay. So that is the idea of a language. It is very similar to what we understand as language. The only difference is in our language, we distinguish words and sentences, but in these languages, formal languages, we don't make such a distinction. Word, sentence, string, all are same. Okay. Any combination of letters is a word or a sentence or a string represented using omega. Okay. And a set of omegas make a language. You can have different languages from the same alphabet set. Okay, that's all. So let me stop here.